Speaker is Professor Greg Chini from the University of New Hampshire. So he's presenting on a-priori, quasilinear modeling, and beyond. So
oh, and which one is the change the slide? Oh, I don't need to. I'll just do it here.
okay being recorded?
Yes, sorry, I should have said. And then to change slide is. Thank you. Thank you. Great. Okay. Well, my thanks to Rich, Beverly, and Dan for the invitation to speak here today. I was politely encouraged to talk about scale-separated quasi-linear modeling, so that's what I will do. As we've heard earlier in the week, the quasi-linear reduction begins with a Reynolds decomposition of a generic flow variable Q into a suitably defined mean. And for shear flows, that's often strategically taken to be a streamwise average plus a fluctuation. And then the key step is that fluctuation nonlinearities are retained only where they feed back on the evolution of the mean fields, but suppressed elsewhere. Now, often the QL reduction is invoked as an ad hoc, but useful approximation. But I'm particularly interested in those cases in which the QL approximation can either be extended to be made systematic, or in which it is formally that is asymptotically justifiable. And this latter scenario frequently arises for systems exhibiting temporal scale separation with comparably slowly varying mean and fast fluctuation dynamics. And in turn, this is often associated with the occurrence of highly anisotropic spatial structures in the flow. Now, of course, there's nothing new under the sun. The QL approximation dates back at least to the work of Herring in the 1960s in the context of Rayleigh-Bénard convection. And Herring, I think for good reason, used the terminology mean field theory. So today I'll attempt to provide an overview of what might be described as rational QL modeling, and I'll show results in the context of wall-bounded shear flows, but also I will make reference to free, strongly stratified shear flows towards the end of the talk. I'll first talk about quasi-linear modeling of exact coherent states and shear flows. These, again, are more properly termed invariant solutions than Navier-Stokes equations. I find it remarkable that certain classes of ECS are describable asymptotically exactly in the limit of large Reynolds numbers by a quasi-linear reduction of the Navier-Stokes equations, known to, I'm sure, many of you as vortex-wave interaction or VWI theory by Hall and Smith, and then subsequently applied for the first time to ECS and shear flows by Hall and Sherwin. So in the first part of the talk, I'll introduce a new class of these asymptotically quasi-linear ECS that may have some relevance to structures in the inertial sublayer of turbulent wall flows, where by definition, viscous effects are weak in the mean. Of course, there's life beyond QL and beyond individual exact coherent states. And one way to extend the QL formulation that is really motivated by the asymptotic thinking is simply to replace the decomposition into mean and fluctuation with spectral filters. And so we separate streamwise modes into low modes and high modes. And then following the spirit of the QL reduction, we linearize the dynamics of the high modes about the low modes. And the merit of this generalized quasi-linear approach is, I guess, twofold. Firstly, in principle, it's systematic in that when the only low mode is the streamwise mean, we are at QL, but by including as many low modes as we would like, we can recover a fully nonlinear DNS. So in that sense, it's at least in principle systematic. Moreover, when non-zero low modes are allowed, new energetic pathways, energy transfers are allowed. And so one of the most important is that a high mode, a linearized mode, could interact with a non-zero low mode to put energy into a different, maybe a neighboring high mode. And so that's a spectrally non-local energy transfer that is completely impossible in QL, and that is important in highly anisotropic shear-driven forms of turbulence. So in that sense, I actually think of GQL as a singular perturbation to QL. Having said all this, I will not say anything else about GQL in this talk in the interest of time. Happy to take questions at the end, and I have a few appendix slides if anyone's interested. So instead, in the second part of the talk, I will discuss a new formalism for efficiently time-stepping slow-fast quasi-linear or generalized quasi-linear systems. And somewhat unexpectedly for us, this shows a different way, opens up a different way for going beyond QL. And hopefully I'll get to that by the end of the talk. Right, so it's long been known now that roll and streak structures exist on a hierarchy of scales in turbulent wall flows, ranging from about an order 100 viscous units for small scale structures near the wall to order H, the height of the boundary layer, or channel half height for large scale structures. And at least for a theorist, it's of interest to ask, is there an asymptotic, possibly quasi-linear, self-sustaining process that could support structures in the inertial sublayer, where again, by definition, mean viscous effects are weak or subdominant. Now, one very striking feature of the flow away from the wall is shown in this plot, which I've lifted from a well-known paper by De Silva et al. And the black curve shows the instantaneous streamwise velocity in a turbulent boundary layer. And what's striking is that the flow seems to segregate into regions of quasi-uniform streamwise momentum. These are called uniform momentum zones that are then separated by internal shear layers or interfaces, what my colleague Joe Kowicki has dubbed vortical fissures. The plot in the middle is some data taken from the UNH flow physics facility, conditional averages through these fissures, and it confirms that the typical jump in speed across one of these fissures is a couple of multiples of the friction velocity. And the plot on the right, which I've lifted from this paper by Joe, indicates that the characteristic fissure thickness normalized by the boundary layer height decays like the friction Reynolds number to the -1/2 power. So the implication is important. That is, as the Reynolds number increases, a greater and greater fraction of the span-wise vorticity in the boundary layer is residing in these fissures. It's as if that's where the boundary layer is. So again, for a theorist at least, that's sufficient motivation for seeking some sort of theoretical mechanistic understanding of these structures. Now, vortex-wave interaction and related approaches really exploit the fact that in turbulent wall flows, comparably weak streamwise rolls having a size, really an amplitude, 1 on Reynolds, can, through the lift-up effect, induce a strong order 1 streak response. That occurs on a time scale that is long, of order Reynolds number, compared to the fast order 1 time scale characterizing inviscid streak instability. So that's the separation in time scales that I had alluded to. And relatedly, or for a related reason, since the rolls are weak, they can be sustained by the nonlinear interaction of streamwise varying fluctuations that are comparably weak. And so then in a self-consistent way, we find that the streamwise varying fluctuations satisfy equations that are linearized about this dominant order 1 streak. And that leads in the largest Reynolds number limit to a quasi-linear reduction that's self-consistent. But there's a problem in applying this formalism to structures in the inertial sublayer, and that is, or can be understood by reference to the streamwise averaged streamwise momentum equation given this sort of ordering. And the point is that if the rolls have this size 1 on Reynolds, then the effective Reynolds number felt by the streaks, and in fact, excuse me, felt by the rolls themselves, is unity. So the implication is that the streaks and rolls are viscously constrained, which is at odds with the mean momentum balance in the inertial sublayer. Essentially, for the same reason, even an upper branch state, so this is EQ2 from an equilibrium state in plane Couette flow that is well described by VWI theory and that superficially has a sort of UMZ fissure-like structure, is really not a good candidate for structures in the inertial sublayer because of the scaling of the rolls. Even as the Reynolds number is increased, these regions of shear will not thin, as shown by this computation from my colleague John Gibson. So with Joe, my colleague Chris White at UNH, and a very good former PhD student, Brandon Montemuro, who carried out the bulk of the analysis, we attempted to develop an asymptotic self-sustaining process theory that could support exact coherent states that have this UMZ fissure-like structure. And really, we considered a surrogate problem. So we imagined stacking identical copies of counter-rotating streamwise rolls in the wall normal direction, but in unbounded plane Couette flow. So if you like, homogeneously sheared turbulence. And this was our surrogate for the inertial sublayer, which has made the analysis more tractable. So our hypothesis was that if the rolls are sufficiently strong, they will be able to differentially homogenize the shear associated with the background Couette flow, and thereby induce emergent internal shear layers, fissures, that have a thickness, capital delta, that decreases appropriately with the Reynolds number. So here the Reynolds number is based on the friction velocity characterizing the jump in speed across the fissure, and L sub y, which is the spacing between adjacent fissures, or equivalently the scale and say the diameter of the large scale rolls in the UMZs. So self-consistently, we find in our theory that the rolls have a strength 1 on Reynolds to the 1/2 power. Note that this is large compared to the 1 on Reynolds sort of threshold for viscous constraint of the rolls and streaks, meaning that our rolls and streaks will not be viscously constrained, but at the same time still small compared to the order 1 streaks that the rolls will induce. So as I've said before, that will automatically lead us to a self-consistent quasi-linear theory, although at the outset that wasn't necessarily an objective. But the story is not quite the usual one, and that's because this shear layer is so exquisitely thin, and that's where all the action is. And so we seek an inviscid inflectional instability, a Rayleigh mode, riding on this shear layer that has a streamwise wavelength commensurate with the shear layer thickness, which is physically reasonable. So that scale is very disparate from L sub y, of course. So this nominally 2D streamwise propagating Rayleigh mode is refracted and rendered 3-dimensional by the slow spanwise variation in the fissure thickness that is itself caused by the spanwise variation of the streak. In the process, the Rayleigh mode picks up fast spanwise variability. And it turns out that this 3-dimensionality is crucial because we're seeking an ECS, so we're looking for a neutral mode. And it turns out that the 2D neutral mode for this configuration is regular, but the 3D mode is singular. And loosely as in VWI, but differing in detail, the singularity is healed within a critical layer that's embedded, in our case, within this already thin fissure. But there's a critical layer mechanism that generates a jump in tangential stress across the layer that drives the rolls, as in VWI. So we're obliged to do asymptotic matching both of the mean and fluctuation fields between these various domains, and then use the WKBJ approximation to accommodate the slow spanwise variation in the Rayleigh mode amplitude A of Z and the Rayleigh mode wave number beta tilde. Of course, I'm not going to go through the mathematical details, so I'll just show you one set of pictures corresponding to an ECS that is supported by our asymptotic self-sustaining process. So here we see the counter-rotating rolls. In fact, there are infinitely many of these stacked vertically. And in color is the streamwise average streamwise velocity. So if we further take a spanwise average of that streamwise velocity, we obtain this step-like profile, which clearly has the UMZ fissure-like attribute. And I emphasize that's emergent. That's not prescribed in our theory. That comes out in a self-consistent way. Again, all of the action is in the shear layers at y equals 0, plus and minus 1, etc. That's where the Rayleigh mode is confined. And if you look carefully, you can see that the shear layer has a thickness that varies slowly in the spanwise direction. That's what causes the modulation of the Rayleigh mode. So because we're seeking an ECS, we treat the fluctuation problem for this x-varying Rayleigh mode as an eigenvalue problem. And again, we seek a neutral mode since we're looking for an ECS. And here I just show some characteristics of the structure of that neutral Rayleigh mode. So this is a sort of vertical slice through the critical layer showing the expected Kelvin's cat's eye streamline pattern associated with the critical layer. And this plot on the right is a planform view. So looking down on the fissure, this is a streamwise, spanwise plane. And you see clear evidence of the, first of all, multi-scale nature of this solution and of the slow modulation, refraction of the wave. In fact, you see these interesting sort of no-fly zones. These are caustics where the fissure has become too thick to support this neutral mode, and those turn out to be important. So I think the merit of this sort of asymptotic construction is it at least shows what is admissible by the Navier-Stokes equations in the large Reynolds number limit. There is a sort of self-sustaining process that exhibits structures, ECS, that have a UMZ fissure-like profile and that satisfy some basic attributes that we would expect to be true in the inertial sublayer. I also think that the analysis is useful in that it shows the type of disparate scale interactions that are possible in high Reynolds number shear flows. Of course, there are a number of questions. One is, it would be great to have some experimental confirmation of the kinematic structure that we have posited in the spanwise wall normal plane rather than just the streamwise wall normal plane. A key prediction of the theory is that the shear layers, the fissures, play an active role in sustaining the UMZs. So that implies upscale energy transport. And it would be interesting if someone could design a clever numerical experiment to kind of explore the veracity of that for turbulent wall flows. And all of this can happen even without walls, I should say, because they really are absent in our model. What we'd really like to do is dynamical modeling rather than just have an ECS, but dynamical modeling that somehow retains the essence of the asymptotic reduction, but we don't know how to do that. So in this next part of the talk, I will move on to discuss a time-stepping methodology for slow-fast quasi-linear systems, bearing in mind that the quasi-linear reduction, as I said, is only useful in the limit of temporal scale separation. But at the end of this discussion, we'll see a way to go beyond QL. Okay, this is the idea is that we would like to time step the slow dynamics only and treat the fast dynamics as a sort of eigenvalue problem. But that's not obviously possible for slow, fast quasi-linear systems with potentially fast instabilities. So I think it's absolutely essential to sort of step back and consider some toy model problems that we can analyze carefully and understand. And that's all I'm going to talk about for the remaining time. So we're going to start with a very simple system, a 2 ODE model that has a slow-fast QL-like character. So U is a slow variable subjected to some slow forcing, Rayleigh damping, and a quadratic nonlinear feedback from this fast variable B. B satisfies an equation that is linear with respect to U, and it's fast if this parameter FR is small. So if U is positive and not changing very rapidly, of course, we expect that B will grow approximately exponentially, and again, if FR is small, on a very fast time scale, until B squared becomes so large that sluggish U can no longer be sluggish and has to respond on the fast time scale, and then we might expect some violent ringing. And indeed, if we just time step this system, that's more or less what we see. You can ignore the red lines for now. But it's instructive to see what happens if we reduce this parameter FR from 1/4 to something much smaller. Then we see, after this violent initial transient, that U settles down to a value that is close to 0. Note the change in the vertical coordinate here. And by inspection of this equation for B, that corresponds to a marginal stability condition. B itself hugs this mysterious red curve. And again, as a theorist, what I would like to predict, at least at 0th order, are these red curves in the limit that FR tends to 0. And so that's easy for this ODE problem. We simply posit that the slow variable is 0, because that's the marginal state, plus some higher order corrections. And then the key point is that the fast variable B must be slave to the slow variable so that it remains marginally stable. In this case, that it remains 0 at leading order. So by inspection of this equation, we simply set B equal to the square root of the forcing, since U is 0, and then we will ensure that du dt, again at leading order, remains 0. And that's exactly how I generated this red curve. Okay, so the two takeaway messages from this very simple example are that slow, fast QL systems that admit fast instabilities rather than just stable waves will self-tune to a state of near marginal stability. Note, I didn't adjust the forcing to achieve this. I didn't adjust a Rayleigh number close to a critical value or something. This is a self-tuning. And that's only possible if the fast field also is slave to the slow field. So that's well and good for an ODE system. What can we do for PDEs? So with Guillaume Michel, Alessia Ferraro, a student of Tobias Schneider and Tobias, we've looked at some model PDE systems. And this PDE system looks a lot like the ODE system that I just mentioned, except that now the slow variable u is a slow field. It depends on a spatial coordinate z as well as on time. Moreover, instead of b, I have a fast field eta, and we've even allowed some weak cubic nonlinearity for the full system at finite epsilon. Okay. So we can carry out a 2-time scale analysis in the limit that epsilon goes to 0. So tau is the fast time, capital T is the slow time. And at leading order, we indeed obtain, almost by setup, I guess, a slow, fast, quasi-linear system. And note here that the overbar refers to a fast time average. So again, the idea is that we'd like to not time step on the fast time scale. So we just want to slow time step this equation. And so we choose to treat the fluctuation problem as an eigenvalue problem with a slowly varying to be determined amplitude, slowly varying eigenfunction, and slowly varying growth rate, sigma. Those are all slowly varying because the mean field, u bar naught, is slowly varying. So all of this only makes sense, of course, if sigma, the maximum growth rate, is non-positive, because in that, otherwise the feedback would blow up, okay? So we're relying on some self-tuning, apparently. If sigma is negative, there's no problem. If sigma equals 0, this average over the fast time is finite. But in that case, we have a new problem, because we don't know how to set the amplitude. Of course, this linear homogeneous eigenvalue problem doesn't tell us anything about the amplitude. And this is where Guillaume had a clever insight, and that was to take a slow time derivative of this leading order eigenvalue problem. And then by imposing a solvability condition, we obtain this equation for the slow evolution, not of the amplitude, but of the growth rate. And that is given in terms of these alpha and beta terms, which are known functionals of the forcing, of the mean fields, and of the eigenfunction. So our algorithm is straightforward. We time step on the slow time scale to update the mean field. And as long as the maximum eigenvalue is negative, we simply set the amplitude instantaneously to 0 on the slow time scale, because the modes would be damped very fast. But if there's a bifurcation, sigma hits 0, then we have to insist, as long as alpha is positive, which would tend to then make sigma positive, which is untenable, we set the amplitude equal to the square root of alpha on beta so that the growth rate remains 0. In the ODE example, it was u itself that was playing the role of the growth rate. You can ask whether this works. The answer for this model system is yes. So here we plot the sort of z-integrated energy of the fluctuation field versus time. And the curves in color are quote unquote DNS. So simulations of the full PDEs for finite epsilon with cubic nonlinearity. We're going to ignore epsilon 0.5, that's too big. But when epsilon is 0.2, we see this violent ringing and then it settles down. Our prediction from our multi-scale approach is shown by this black curve. The dashed black curve shows the evolution, slow evolution of the leading eigenvalue. So while the eigenvalue is negative, the energy amplitude of the fluctuations is 0 according to our algorithm. But as soon as the eigenvalue hits 0, we then set the amplitude according to our prediction to this value, and we adjust it accordingly. And you can see it beautifully filters the ringing and accords with the full simulations at epsilon is 0.02, but we can take very big time steps. Again, that's a model problem. We have implemented this algorithm recently in a much more challenging problem, namely two-dimensional, stably stratified Kolmogorov flow. This is a body force shear flow. And I won't go into the details, but for these parameters, our algorithm converged to a steady state that might be called an exact coherent state shown here. But I want to draw your attention to this picture, which shows the final, the growth rate versus now horizontal wave number, because we have a two-dimensional system now. And in addition to insisting that we have this zero eigenvalue, it has to be a maximum over all wave numbers for self-consistency. So that's a new wrinkle that needs to be enforced. That potentially would be computationally expensive, doing lots of eigenvalue problems to make sure we're tracking the local max. But thanks to Alessia's very hard work, we can now predict the slow evolution of this marginal wave number. So there's natural adaptivity here as well. Moreover, for different parameters, it's conceivable we might get another marginal mode. And because of the quasi-linear structure of our system, there's sort of a nonlinear superposition that is feasible. The modes only talk to each other through the mean. So we could simply introduce a new amplitude and a new wave number in a straightforward and scale selective way. The last thing that I will say is, how do we go beyond QL with this approach? Well, what we found in the stratified flow simulation problem was that we could have a sigma equals 0 state in which alpha is positive, and everything is fine as long as beta is also positive. But if at some slow time instant beta becomes negative while alpha is positive, then the modulus of A is not defined. That actually tells us something physical, right? That says that the feedback from the fluctuations would further destabilize the mean field. It's telling us that quasi-linearity and scale separation are completely lost, and the slow field's going to respond rapidly because the fluctuation amplitudes become large. You can no longer ignore fluctuation nonlinearities in the fluctuation equations. So this is actually a virtue, because we have an asymptotically adaptive way, is by tracking beta, to know when to switch to a full nonlinear solution of the PDE, or better yet, to switch to an epsilon-free rescaled version of the PDE that's valid for large fluctuations, and that lets us take big time steps. But in any case, we only need to do this until we hit another marginal stability manifold, as shown in this diagram and as shown in these figures. So we considered another 1D toy PDE model where beta could become negative, and we found instances where we were on one marginal manifold and could basically do QL with our eigenvalue approach. But then beta went negative, and so we had to switch to DNS. You can see that the growth rate is now positive, but it comes back down to 0, and then we land on another marginal stability manifold. So I will conclude by saying perhaps this points to a way for doing something like dynamics with exact coherent states. Thanks very much.
Greg, I mean, can you say something more about this inverse cascade that you implied when you said that the fissures drive the...
Oh, yeah. So, okay. So all I mean is that the large scale roll motions, which sort of exist within the UMZs in our construct, are actually driven by, stresses from very small scale Rayleigh modes. So that, yes, yes.
From the edge of the...
Yeah, it would be from the skin of the fissure. So that's small scale to large scale driving is all I'm saying.
So how is that? I mean, do you understand how that happens? I mean, what breaks the symmetry basically? You have this thin thing that...
I'm not sure I understand which symmetry you're talking about. Sorry.
Well, I mean, you have this thin layer.
Yep.
That doesn't know what is right or left, I assume, but then decides that he wants to go to the right.
Right. Are you talking about the Rayleigh mode refracting?
Something like that, yeah.
Yeah. I mean, it's clearly retained some symmetry, right? I mean, these are essentially oblique modes, right? Symmetric about the streamline.
But I mean, there are many of these wires that way, and then they want to drive a roller that goes to...
Oh, I see what you're saying. Sorry. Yeah, so that's one way in which I mean, I don't think I can give a physical explanation, but sort of the mathematical comment is that this differs also from VWI in that, of course, it's a divergence of a stress, right, that gives rise to the force. And And the divergence here is a divergence on this slow z scale. Somehow it's some integrated effect, averaging over many of these wavy oscillations. But I don't probably have a good physical answer for why that is, pushing one way versus the other. I'll think about
Are you staying longer here than?
I am staying for a long time.
Okay.
If they don't kick me out.
Thanks, Regan. That was a very interesting talk. There's a lot in there, and I'm going to talk to you later about the last part.
Yep.
The first part, your diagram for the UMZs.
Yes.
So it suddenly occurred to me, are you finding 3D ECS for a mixing layer?
Yeah, that's how good question. And that's how, when I was talking to Joe about this, I was thinking, my thought was to think exactly of a mixing layer. But the difference is the mixing layer has these rolls keeping it there. So it's actually a strained mixing layer. And that's the problem that I think is worth analyzing. And I'd love to
So you have to have an external flow in between.
Yes.
Got it.
That's
okay.
So I think that problem on its own is still worth picking apart and thinking about the dynamics in the shear layer. There could be I've been preaching QL, but there could be nonlinear dynamics within that shear layer that could be modeled in an interesting way.
And just continuing the analogy with the mixing layer, these structures are linearly stable, are they?
What do you mean by these structures?
Well, a mixing layer, if it's unstratified, is
going to roll up.
Yeah.
Yeah. So, well, that's where the fact that the layer is strained, I think, is very important.
Okay.
But at the same time, I would love for Ivan or someone else to get some measurements, not simply in the streamwise, wall normal plane, right, but in the spanwise wall normal plane, to see if any of this kinematic construct accords with reality.
Right. Okay. Well, that's recorded. That request.
Okay.
Okay.
Let's thank our
Okay.
speaker again.
Thank you.